Hi, I'm Gopika Sudhakaran and welcome to our ICCV 25 poster on Adaptive Relation Tuning for Generalized Relation Prediction, a joint work with Hikaru Shindo, Patrick Schramowski, Simone Schaub-Meyer, Kersting, and Stefan Roth from TU Darmstadt. Visual relation detection first detects objects in an image and then establishes pairwise relations between them. We assume objects are known, so the focus is on relation prediction. The first challenge is overfitting to in-distribution relations. For the given image and its objects, A represents the ground truth, B and C represent the predictions of VLMs tuned for relation prediction. However, even the VLM fine-tuned using the balanced data still biases towards frequent seen predicates. Here, naivety means a VLM naively fine-tuned on relation data. The red highlights show mispredicted relations reflecting the in-distribution bias. The second challenge is the inability to infer novel unseen relations. BRD benchmark annotations are incomplete with missing potential relations. For instance, for the same image and detections, the ground truth lists boat in water, water below sky, and boat below sky. But we are not limited to these. Equally valid descriptions include boat floating on water, water reflecting sky, boat against sky, or water under sky and boat sailing under sky. However, the relation-tuned VLMs often fail to predict such novel or unseen relations. Our third challenge is coarse ground truth. Consider the phrase man holds beer. Which image does it describe, A or B? Most would pick A. For B, that label is too coarse. A more precise relation for B is man drinking beer. However, the ground truth for B still says man holds beer. So when a model predicts drinking and is penalized for not saying holding, we discourage fine-grained understanding and herd generalization. To address the challenges, we introduce ART framework. It has a data creation stage and an adaptive relation tuning stage. Let's dive into each stage in detail. To create relation tuning data, first we organize predicates into its high-level relation types such as spatial, semantic, and possessive, depicted with example relations. These are the three axes of scene understanding, covering geometry, activity, and position. The core idea is that pairs often carry multiple high-level types. By hinting the relation type, we narrow the decision space and thus partially addresses the coarse relation challenge. For instance, given two objects, person and TV, they can have a semantic relation watching, which doesn't convey anything about the spatial orientation if the person is near or far from the TV. Thus, both relations are crucial for better scene understanding. Further, to partially tackle the challenges 2 and 3 of incomplete and coarse ground truth, we introduce a counter-negative mining approach that selectively assigns negatives based on the relation type. Treating unlabeled equal to negatives penalizes fine-grained answers. Hence, for each positive response categories, we assume the mutually exclusive negative response categories. Let's see an illustration of why spatial and semantic are treated as negatives for possessive. For the given image, person and hat has a possessive relation wearing. Here the spatial orientation is implicit, while action verbs are less relevant, as position describes a static state. This leads to our final question-response template. Our instruction set ablations reveal that without high-level relation types and negative mining, both R and MR are lower. Adding high-level relation types gives a small lift to R and MR. Adding one random negative per sample improves them further. Replacing random negatives with counter negatives produces a clear gain in both R and MR. To reduce overfitting to in-distribution relations and to enhance unseen relation predictions, we propose ART. We start with the relation tuning data and run balanced sampling, taking a small even percentage from each predicate to form S-train. The remaining data becomes a pool, S-pool. We tune the VLM on S-train, then run inference on S-pool using uncertainty and dissimilarity modules, where we compute entropy and similarity scores on the pool. Then we start adaptive sampling. Firstly, we do adaptive thresholding by fitting normal distributions to entropy and similarity scores. Secondly, we define a set of selection rules, which ensures entropy is used to upsample informative samples from uncertain true positives and false negatives. On the other hand, similarity is used to downsample semantically rich false positive predictions deviating from the ground truth. Then we update S-train with new samples and remove them from S-pool. We repeat this until the total budget is met. Evaluation of generalization of art. The performance on mean and generalized mean recall metrics are crucial for generalization, as these metrics evenly reflect the performance on the full predicate distribution. Art model variance outperforms all its baselines on both the metrics. Coming back to our intro figure, art predicts detailed context-rich relationships unlike ground truth, thus enhancing downstream reasoning. For additional details, please find our paper and code online.